Hello class, this is CSE-5250, Section 1, Week 15, Video 11, Spring 2023, and where did the semester go? It was just yesterday that we were just starting off the entire class, and now it's almost already summer. I hope you have good summer plans. I know I do. Anyway, before we begin, please note that I've graded all the assignments, except for two, and those are our final two upcoming assignments. The first one is the MPI-based Sieve of Eratosthenes, which I made due the Wednesday of finals week instead of the Monday of finals week. The second one is a short answer question that's going to be due sometime this Friday that I will reveal within this video. So, what I'm going to talk about now, I've graded everything. Make sure the grades are appropriate for what you've done. If you've noticed any discrepancies, let me know so I can correct them as soon as possible. Anyway, for this video, we're gonna look at a few closing notes about the course. Why parallelism? Why parallelism? Why we have to consider it? Why can't we just wait for computers to get faster? And another thing is, do we have anything that's general purpose enough when it comes to parallelism? Anyway, let's begin with the supplemental notes that Dr. Gomez provided from when he was teaching the course. Dr. Gomez previously taught the course in earlier years, and I've adapted his notes to fit a PowerPoint format. So, let's look at those notes. Why parallelism? Because some problems are just way too big to solve in a reasonable amount of time, but they're such that we can break it up into smaller chunks, work on each chunk at the same time, and then merge it all back together in the hopes that if it's done right, we will have solved that problem in a fraction of that time. But that all depends on whether we can. That all depends on how many chunks we can divide it up into. Some problems that are too big to solve in a reasonable amount of time may be solved by splitting it into pieces, working on each piece concurrently, and then merging them back together. Some problems aren't like that. But if we're lucky, we might find a few problems that can be solved this way. Can't we just use a fast enough computer? Well, I would be getting a little bit ahead of myself, but couldn't we just wait for it to solve? Well, wait for what? I didn't specify what we're waiting for, but I guess there are two ways to answer that question. Can we just wait for the computer to solve the problem? Or can we just wait for a faster computer to come along to solve the problem for us? Well, in the case of just waiting for the program to solve, keep in mind that might work for some problems if you're really patient, but not so much with problems with exponential time complexity. If it takes like 1 month to solve a problem of size 1, and it takes twice as much to solve a problem of size 2, twice as much of that to solve a problem of size 3, that's an exponential time complexity. So, size 4 takes 18 months, size 5 takes 16 months. You get the idea. It grows exponentially, and the larger the problem becomes, it just takes in more and more time. Could we just wait for a faster computer to come along and solve it then? In computer architecture, there are two things to consider: speed and throughput. Moore's law, which isn't really a law but more of an observation, it's this observation that says processing speed doubles every 18 to 24 months, depending on the definition. I've seen 18 months, I've seen 24 months. We could wait for processing speed to catch up, but the thing is, if we were measuring Moore's law just by processing speed alone, then Moore's law should have been already dead at least 20 years ago. My family's first computer was this compact COMPAQ something or other computer, and I think it was like a dual core CPU that ran at 2 gigahertz. I forget the specs, it was so long ago. But my current computer is even though I did not put in that Ryzen 9 yet, my computer is only just a little bit faster in terms of clock speed. So if we're going by clock speed alone, then Moore's Law is dead. So why can't we just make our computers faster? Well, for several reasons. One of them is to make a computer run faster, or rather, faster computers correlated to how we can shrink transistors on a CPU to be smaller and smaller and smaller. Right now, we are at 5 nanometer node size for our CPUs. For a while, it was 14 nanometers, but recently it got as low as 7 and now 5 nanometers. So the idea is by making these transistors smaller, we reduce the distance it takes for signals to travel. But the end result will be one of two things. You can do the same amount of instructions per clock cycle using less power, or you can do more for the same amount of power. So can we just jack up our clock speed? That's called overclocking, and even overclocking has its risks. If any of you have built your own computers, there's a good chance that you will have tried overclocking, or at least know what it is. I used to overclock my computer, but then every time I visit my parents' place, I bring my computer along, and I have deduced that my computer always crashes when it's overclocked. So I can't really overclock anymore because of that. So instead of my 3600 megahertz or 3.6 gigahertz, it's now at the base clock speed of around 3 gigahertz. And I deduced that was because my computer is just getting older. Maybe I'm at the point where my power supply cannot supply enough power to my CPU. And that's one thing to consider about overclocking. You need enough power. You need to feed enough power to the CPU itself. You also have to keep it cool. When it comes to overclocking, you need like big, beefy cooling systems. So you need like a really big air cooler or maybe an all-in-one liquid cooler. But if you're really a hardcore overclocker, it might reach the point where you need to add an actual refrigeration system onto the CPU itself, because it just puts out so much heat. And it turns out that heat output is exponential too, so we can't really overclock. At least not easily. The record for overclocking was performed on an AMD CPU, and it was at least 8 gigahertz, and then what it took was liquid nitrogen and tons of insulation. Liquid nitrogen, because it's the only thing cold enough that would keep the CPU cool it's the only thing cold enough that could keep the CPU cool. And the insulation was because with liquids that cold, you risk having water condensing on the motherboard. You risk having water condensing on the components themselves. And zap, you would electrocute the entire system. So we can't rely on speed for those reasons, among others. How about making our transistors smaller? Well, at some point, if you think about it, we'll reach a point where if we just keep shrinking our transistors, At some point, we'll have transistors that are the size of one single atom, and we can't really make it any smaller than that. Atomos, Greek for indivisible. So we can't make it any smaller. Unless we tried some other material in which we can make our computers even smaller than that. But what can be smaller than an atom? Quarks? Can you make a CPU out of quarks? Can you make a transistor out of quarks? How can you do that? Anyway, at some point we're gonna reach a limit with how small we can make our transistors. If we haven't reached such a limit yet, because before then you would have to contend with quantum tunneling, which is where the signals just jump, or rather, the electrons just literally teleport from one closed gate to another. It's supposed to be closed, but the electrons manage to jump the gap anyway. So yeah, issues with quantum tunneling, the fact that we can't make our computers any faster without literally melting them down, means that if we want to increase processing speed, we can't do it by speed anymore, we have to do it by throughput. And that might just be why, in recent years, we've been seeing this, I don't know if you can call it a renaissance, but let's call it a renaissance. We've been seeing this renaissance of high core count CPUs. The Ryzen 9 that I still have on my shelf that's a 16 core, 32 thread behemoth that I still have yet to install in my computer. Intel has a competing product that still edges out in terms of speed versus throughput. Intel also infamously debuted this CPU that took a 1 horsepower cooler just to keep cool. And what's so scummy about that is they never divulged that to the audience. But anyway, at least now Intel has these CPUs that can overclock to at least 5 gigahertz, and so does AMD. So maybe we are making advancements in terms of speed, but it doesn't feel like much. Anyway, and without parallelism, there have been a few problems that could only have been solved using parallelism. Without that, it would just feel like it was downright impossible. So difficult so as to be impossible. But difficult doesn't necessarily mean impossible. I mean, if you've ever solved one of these things before, the first time you see one of these, you might think to yourself, there's no way I'm gonna solve one of these. But then you go to YouTube and find tutorials on how to solve it, and then after a while, you either do the beginner's method or you stumble upon your own algorithms and write them down. And then, sooner or later, you can solve one of these no problem. Not necessarily fast, but you can solve it, and at least there's that. There was the one example of a Minecraft seed. In Minecraft, there was this image there was a thumbnail image that someone wanted to find a seed for, and that effort, which was documented by a YouTuber by the name of SalC1, he documented that entire process, and it took 8 months and all sorts of innovations just to find the seed. But that's the thing, they found the seed. So what it took for that one example was, well, it was solved in part using parallel programming, but that was just to whittle down the possible space of like 281 trillion seeds. They had to whittle that down to something that was small enough that could be brute forced within a reasonable amount of time. And yes, they did find the seed. If you go through those videos right now, and you'll have to load the appropriate Minecraft version for this because it doesn't work for newer versions. If you load if you load the right Minecraft version and type in the seed, you will find the exact same hill that was featured on that Minecraft thumbnail. Anyway, but what do we have then? In terms of parallelism, we have 5 main models of parallel computing. One of them isn't really parallel computing. The first one is single instruction, single data, and that's just every sequential program we have probably written to date prior to the class. My face is in the way. I'll put it down here. We have multiple instruction, single data, different code or different processes, but they're all working on the same data. So this would be a backtracking algorithm in parallel. Single instruction, multiple data, that is where loop parallelism would fall under. That is something that NVIDIA CUDA is able to do. And the most general of them all is multiple instruction, multiple data. And there's the fifth one that straddles 2 of these categories, and that is single program, multiple data, and that is where task parallelism is. So OpenMP is capable of doing, well, loop parallelization as well as task parallelization. You can write an if statement that says thread 0 does something else from all the other threads, for example, and that would be task parallelism. Loop parallelism is what we were doing by adding that compiler directive, the OMP parallel 4. Loop parallelism is exactly what we're also doing with the MPI set of Eratosthenes. And loop parallelism is something you can also do with NVIDIA CUDA. Even though I didn't require you to write anything in NVIDIA CUDA, because out of concerns that the hardware might not be usable in the Jack Van Hall computer labs, I at least showed you in last week's video what the code and execution would have looked like. So yeah, the other thing is these models require specialized hardware. OpenMP can run on just any computer that has a CPU. What am I saying? Every computer is going to have a CPU. But the higher core count, the better. CUDA programs require a discrete NVIDIA graphics card to run, and MPI, it turns out that MPI is meant to run on multiple computers, but it turns out that we can run it on just one computer and it will still work. We have the concern that by running it on one computer, we are limiting MPI's potential. But that potential requires like an entire network worth of computers. So, yeah. Also, how hard is it to get the necessary hardware in the first place? If your computers have like one of the high-end CPUs in them, like a Ryzen 7 or Ryzen 9 or an Intel Core i9, one of those parts is the cost of one of those parts is like pretty high. I'm just gonna say it's pretty high. But the same goes for graphics cards. And then how much more to building out what's basically building a network of computers. Anyway, for some of these implementations, you don't need specialized hardware, but it helps if you have it. But at what cost? So basically, if you can allow for dozens, hundreds, maybe millions of threads of execution to be executed at once, the better. any CPU made any computer with a CPU that was made within the last couple years will be able to do that. I would bet that the minimum right now is 4 cores, 8 threads. When a couple years ago, that was the maximum. Of course, the high core count CPUs are not at all cheap, unless you get them used. At one point, no wait. Yeah, anyway. Just look at the hardware lineup of either Intel or AMD. You'll see this trend of increasing core counts starting around 2017 because that was when AMD first announced their Ryzen CPUs. And I guess you could say I'm a little bit biased towards Ryzen CPUs because, well, that's what I know. That's what I know, and because of that, I really don't know too much about the Intel lineup, but it's only because I've had a hard time trying to understand the Intel lineup. But it's only after that I built my computer that when AMD was doing their Ryzen 3, 5, and 7, that they were basically more or less mimicking Intel's Core i3, i5, and i7 lineup. Things got weird when we got the Ryzen 9s and Intel Core i9, and then the Threadrippers. But anyway, I guess it's safe to say that now we have computers out there with high core count CPUs. But now, what does it take to program one of these things? In the case where you have a multi-threaded program, that's actually a really easy way. That's the easier of two ways of having processes, I guess in this case threads, communicate with one another. So, inter-process communication is achieved in one of two ways. The first one is if you have shared memory. You only need to do message passing if the two processes are on separate computers. So that's what MPI does. It's a message passing interface. And again, it's meant for having programs parallelized, but having processes separated on multiple computers. So that in theory we can just run way more processes than if it just was one computer. So, which one is best? I guess it all depends. It depends on what you have. It depends on how easy it is to program it in the first place. It depends on what hardware you can easily acquire. Or you might just get lucky and realize, hey, I have this such and such graphics card. We may as well use it. There's no one model or language or hardware to rule them all. Though some problems can be solved more easily, I guess I should say faster, on certain hardware. But at what cost? The cost of having to convert or rewrite an entire program? How much is the hardware though? So yeah. When it comes to parallel programming, there are several ways of making parallel programs, but no one method is truly best because it all depends on what we're trying to do. And for some of you who wrote that as your answer for the midterm assignment and for one of the short answer questions as well. And yeah, it all depends. What are we trying to do? Does everyone necessarily need to have a Ryzen 9 in their computers? Probably not. Maybe if you have a legit use case for such a monster of a CPU, then yeah. But for anyone else, I think if it were me to answer the question of how many CPU cores is enough, I'd say 4 cores, 4 threads, absolute minimum. What was once the maximum of yesteryear is now the minimum. So, here is the last short answer question for the entire course. Where do you think Moore's law stands? Will it continue to hold up in the future? What I can do right now is give you a bit of a head start on how to answer that question. So if we go to Wikipedia, once upon a time all my teachers told me don't use Wikipedia as a source, but I guess this is now common knowledge. You can use the sources that Wikipedia uses. So Wikipedia is good in the sense that it's a springboard to get you started on actual research. So Moore's law is this observation that the number of transistors on an integrated circuit doubles about every 2 years. The definition I was personally familiar with was based on clock speed, and if we're going by clock speed alone, then Moore's law is dead. So these days we're probably going by transistor density. Can this continue? Remember what he said about exponential growth? This is also exponential growth. If you have a lake full of invasive lily pads that grow really fast, like suppose these lily pads, the amount of lily pads in the lake doubles every day. So on the day when you have 50% of the lake covered in lily pads, when will the lake be completely full? Under the assumption of unimpeded exponential growth, by tomorrow, that lake will be full of lily pads. 100% full of lily pads. But what will happen at the day after that? Well, unimpeded exponential growth will say we should have twice as many lily pads. But now, where do they grow? On the land? What happens more in real life is we don't have truly unimpeded exponential growth. You have limited resources. Thanos did have a point when he said the resources in the universe are finite, but you don't have to cull off half the world's population to keep that in check. The population can do that itself. So in the example where we had 50% of the lake covered with the lily pads, what would realistically happen is it would slowly grow to cover the entire lake. It wouldn't be fully covered by tomorrow, or at least it wouldn't necessarily be, because competition of resources, and is there an animal that will eat the lily pads? Some of the lily pads will die off, some of the lily pads will die off due to old age, so you have to account for that. But basically, in nature, there is no unimpeded exponential growth. So what does that say for Moore's law? Will we reach a ceiling? Well, if you go a little bit further down, major enabling factors for Moore's law, integrated circuits, among other things, recent trends, not threads, forecasts, and roadmaps. Gordon Moore stated back in 2005 that this projection cannot be sustained indefinitely. It can't go on forever. Transistors would eventually reach single atom size. Even before then, we would still have the problems of quantum tunneling. So, in 2016, this organization, or the ITRS, after using Moore's law to drive the industry since 19, reversed its final roadmap. It no longer centered its research and development plan around Moore's law. Instead, it outlined what it might be called the more than more strategy in which the needs of applications drive chip development rather than a focus on semiconductor scaling. So basically, that sounds like you have specialized chips rather than general purpose chips. So instead of having a CPU that can do all sorts of instructions, you would that sounds like you have specialized chips that only do one instruction, but it does it really, really well. NVIDIA CEO Jensen Huang declared Moore's Law dead in 2022, though Intel CEO declared that it wasn't. So is Moore's Law dead, or is it alive? Is this a Schrodinger's cat situation? Is this Schrodinger's Moore's Law now? Does looking at the data determine what our output becomes? Or are we just cherry picking good examples and declaring, hey, Moore's Law is holding up? What do you think about that? Okay. And that isn't even considering what's going on in the manufacturing department as well. Research and development towards making transistors smaller. It turns out Intel for a while had some problems trying to do that. Look into that for yourself. I just know that it's a thing. Anyway, that's gonna be it for the entire course. So, yeah, basically this is the final video. And where do you think Moore's Law is gonna be? Alright. That's it. That's the entire course. Alright, so answer that question and finalize the sieve of Eratosthenes using MPI. And that's basically it for the course. Thank you, class. Thank you for a good semester. Alright, see you later.